we have y written as f of x. Y is an explicit function of x. I know the exact rule so that I get a value of y from some value of x. Well, suppose instead I have some function of x and y equaling 0. Then we say that y is an implicit function of x. Somehow, y here does depend on x. We just don't know exactly how it depends on x. It's some relationship, some rule. So if I write y equal x cubed, then we say that y is an explicit function of x. But if I write x squared plus y squared equals 16, then y here is an implicit function of x. Somehow, y here is related to x, but you may not know exactly. And you may have that you can only represent y as a function of x in some little local neighborhood. So, of course, this is quite easy. Maybe with something more complicated. So maybe you have something like x tangent x plus y to the power secant y is equal to x squared minus tangent y. Well, y here is some function of x, but I have no idea how it's related, how it is related to x. You can't really solve a problem like this. It's just too complicated. So if I have an explicit function, say y equals x cubed, I can find its derivative. Now the question is, so if y equals x cubed, then y prime is 3x squared. Now the real question is, well, can I find the derivative when y is an implicit function of x? So can I find the derivative of y when y satisfies, let's say, this equation? The answer is yes. Just use the chain rule. So let me give you the technique by example. Page 166, problems 5 through 20. Find dy over dx by implicit differentiation. So when we find the derivative of a function written implicitly, then we call this implicit differentiation. Okay, so I have here that 2x squared plus xy minus y squared is equal to 2. Let me take the derivative of both sides of my equation. And so the derivative of x squared is just 4x. Assume that y is some function of x. I don't know what function of x it is, but it's some function of x. So to take the derivative of xy, well, both x and y are functions of x. Therefore, in order to take its derivative, I have to use the product rule. And so it's equal to the derivative of the first times the second plus the first times the derivative of the second. Well, I don't know what the derivative of the second is. It's, well, the derivative of the second, dy dx. Plus, well, let's take the derivative of the next term, minus y squared. Well, again, I can use the chain rule, the general power rule, to take the derivative of y squared, bring down the exponent out front, rewrite what's inside to the power of 1 less, times the derivative of what's inside. Is equal to, well, the derivative of 2 is 0. And now you can solve for dy dx. I can group everything that involves dy dx, let's say on the left-hand side of my equation. Let me factor out dy over dx. And let me bring everything that doesn't involve dy dx to the other side of my equation, minus 4x minus y. And let me divide both sides of my equation by what's in front of dy dx. So I get that dy dx equals, I don't like negative signs, so maybe I'll switch all the signs around. 4x plus y over 2y minus x. I changed all the signs. Any questions about that? So now you have determined what dy dx is. Notice that the derivative depends both on x and on y. Since your original function depended on x and y, you can't really expect that your derivative is going to just give you a function of x. Any questions about this? Okay, let me do problem number 18. So again, we have x sine y plus y sine x is equal to 1. I want to find the derivative of this. I want to determine dy dx. So let's take the derivative of both sides of my equation. Let's use the product rule. The derivative of the first times the second plus the first times the derivative of the second. The derivative of sine of y is cosine of y times the derivative of what's inside. The derivative of y is dy over dx plus the derivative of the first. Well, the derivative of the first is just dy over dx times the second plus the first times the derivative of the second. The derivative of sine of x is cosine x is equal to the derivative of 1, which is 0. Let's collect all our terms here. And so I have x cosine y plus sine x times dy over dx is equal to minus sine y minus x cosine y. Divide both sides of your equation by what's in front of dy dx. So this is equal to minus sine y plus x cosine x plus x cosine y all over x cosine y plus sine x. And that's your answer. Any questions about that? Any questions on that? Okay. Let me do in problems 25 through 32, use implicit differentiation to find an equation of the tangent line to the curve at the given point. Problem 30, x to the 2/3 plus y to the 2/3 equals 4. The given point is the point -3, radical 3, comma 1. This figure here is actually called an asteroid. Something like that. It looks something like that. And so first, I guess let's find its derivative. So let's first determine the derivative. So I have here x to the 2/3 plus y to the 2/3 equals 4. So let me take the derivative of both sides of my equation with respect to x. So the derivative of x to the 2/3 is 2/3 x to the -1/3. The derivative of y to the 2/3 is, by the chain rule, bring down by the general power rule, bring down the exponent out in front, rewrite what's inside the parentheses, the power of 1 less, times the derivative of what's inside, dy over dx. The derivative of 4 is 0. And I want to determine the slope when x is, at the point -3, radical 3, 1. So let's determine the derivative or evaluate the derivative. Let's say that. At the given point, -3, rad 3, 1. So wherever I see an x, I'll replace x by -3, rad 3. Oh, that's horrible. And where we see a y, I'll replace y by, here's a question. Why is that 1/2? Okay, so that's 1/3. Replace y by 1 times dy over dx. And then solve for, well, dy over dx. The 2/3 cancel. You multiply both sides of your equation by 3/2. So I'm multiplying both sides of my equation by 3/2. So that the 2/3 cancel. And so this is just equal to, so dy dx, and of course, 1 to the -1/3 is 1. So dy dx at the point -3, rad 3, 1 is going to equal, we'll bring this to the other side. When I bring this to the other side, it changes its sign. So it's equal to 3 rad 3. Oh, maybe I should write that. I'm going to rewrite that. 3 rad 3 is 3 to the 3/2.
Excuse me, Professor?
So the 3's cancel. So this is 3 to the -1/2. And so the slope is 1 over the square root of 3. Okay. And so I have a slope. I also have a point. So I can use the point slope form for the equation of a line. And so y minus y1 equals m x minus x1. So I have y minus. Y1 in this case is just 1. equals m. M in this case is 1 over rad 3. And x in this case is a negative 3 rad 3. So this minus becomes a plus 3 rad 3. Which actually, if you, and I don't need to, if you wanted to multiply inside the parentheses, then it simplifies because the rad 3's cancel. But I'm not going to simplify it because any further, because it's already in one of the forms for the equation of a line. And so this is the equation of my tangent line. Any questions about that? Okay. And so let me do problems 35 through 38. Find y double prime by implicit differentiation. Problem 36. X squared plus xy plus y squared equals 3. Okay. And so let's find the first derivative. X squared plus xy plus y squared equals 3. So let's differentiate both sides of my equation. Derivative of x squared is 2x. In order to take the derivative of xy, I'll use the product rule. Derivative of the first x, derivative of x is 1, times the second y, plus the first x, times the derivative of the second, derivative of y is dy over dx, plus. So that I found, well, derivative of x squared, which is 2x, derivative of xy, which is y plus x, x plus y prime. And now let's take the derivative of this term. Well, I'll use the general power rule. I'll bring the exponent out in front. Rewrite what's inside. All times the derivative of what's inside. Is equal to the derivative of 3, which is 0. And so I have, collecting terms, x plus 2y dy dx. Just writing the terms that involve dy dx on the left-hand side of my equation. And let's bring these that don't involve dy dx to the other side of my equation. Minus 2x minus y. And now let's solve for dy dx. So let's divide both sides of my equation by x plus 2y. So that's the first derivative. Now let's find the second derivative. So find the second derivative. This is going to be the derivative of the first derivative. So this is going to be the derivative of, well, I found the first derivative, negative 2x plus y over x plus 2y. Use quotient rule. So now I'm going to use the quotient rule. And so this is equal to derivative of the numerator, which is 2 plus, so derivative of 2x is 2, derivative of y is y prime. Maybe I'll just use a y prime here, make it look more like a prime, y prime. So that's the derivative of first, the numerator times the denominator minus the numerator. By the way, I left this negative out in front. So the numerator doesn't involve any negatives. All times the derivative of the denominator. And so the derivative of x is 1, the derivative of 2y is 2y prime. And so 1 plus 2y prime, all divided by the denominator squared. Now, you have to plug in, oops, here it is. Now you have to plug in what y prime is. Y prime is this. So wherever I see a y prime here, I'm going to have to replace y prime by this. And so it's equal to minus 2 plus y prime, which is a 2x plus y over x plus 2y. All times x plus 2y. Plus, minus 2x plus y times 1 plus, it's 2 times y prime, but y prime is negative, so I'll put a negative here. So minus 2 times, 2 times y prime, which is 2x plus y over x plus 2y. All divided by my denominator, x plus 2y squared. So this is equal to, well, in this first case, I'll multiply the x plus 2y inside the parentheses. So if I do that, I get, and I'll keep the minus out in front. So I'll keep this minus out in front. So I have here 2 times the x plus 2y is 2x plus 4y. Minus, well, the x plus 2y's cancel. So you get a minus 2x minus y. So that's your first term. Minus. So I'll multiply the two x plus y inside the parentheses. And so I get 2x plus y, I multiply by 1, minus 2, times, well, this will be a 2x plus y quantity squared over x plus 2y. Okay, so this is equal to, I guess I'll keep it this way for a second, so minus. The 2x's cancel, and so I get 4y minus y is 3y. Minus. Let's get a common denominator, this last guy. So this is x plus y, x plus 2y. And I'm going to have to multiply this times that. And so I get 2x squared I get 2x times 2y is 4xy plus another xy. So that's plus 5xy. And then lastly, y times 2y is plus 2y squared. Minus, let me multiply out 2x plus y quantity squared, so that's a 4x squared plus 4xy plus y squared all over, well, luckily the common denominator. All divided by x plus 2y. Quantity squared. Okay, so this is equal to negative 3y minus all divided by x plus 2y squared. And this is an x, well, I'll just leave it as x plus 2y. Okay, so I have here 2x squared minus 8x squared. So that's a minus 6x squared. I have here 5xy minus 8xy. So that's a minus 3xy. And I have here 2x squared, I'm sorry, 2y squared minus 2y squared. So those cancel. So actually, I don't have anything else remaining here. Oops. Here. So let me get rid of the denominator. So let's multiply and divide by x plus 2y. And so this is equal to minus. So let's multiply the 3y times the x plus 2y. So that's a 3xy plus 6y squared. The x plus 2y's cancel. So these are going to change both of these signs to pluses. So plus 6x squared plus 3xy all over x plus 2y cubed, since there are two of them plus another one of them. So you finally get is equal to minus 6x squared plus 6xy plus 6y squared over x plus 2y cubed. And so finally, you get that the second derivative is negative 6x squared x squared plus xy plus y squared over x plus 2y cubed. Any questions about that? Okay, so that's your second derivative. I guess the hard part is simplifying it to something where it looks at least decent. I just sort of am prejudiced against leaving it as this complex fraction. So I don't like the fact that it was a complex fraction here. And so because of that, I felt compelled to simplify, which unfortunately meant do work. Any questions about this? Okay. And that's it. Any questions? So if you notice that really we didn't do anything different, it was more almost notational that we just sort of said, we're using the chain rule, right? And so this implicit differentiation is really just an application of the chain rule.